Yeah, good evening.
Yeah,
I think we start.
Yeah, let's start.
Okay, good evening and a warm welcome to everyone to WeldTech Talk 21. We are really happy to continue with the WeldTech Talk. And today again, we have our dear friends Gary and George to help us with the common mistakes made and for corrosion resistant products. It's going to be a very interesting evening. Once again, a warm welcome to everybody. I see that it's 5 exactly. We've got about 84 participants and more joining in. So at Sigma Weld, we are very glad to be a part of WeldTech Talk and continue to support it for the next 3 years. Over the next couple of days, we will also introduce a bot which will share all the links for all the participants to view the past videos as well as the ones. It will be also an informative bot which will help you connect and keep in touch with the upcoming events. So without wasting much more time, I would really like to invite all our guests today. And Dr. Christian, if you could take over and introduce George.
Yeah, thanks, Nimesh. And a warm welcome to all those who have joined today, Gary and Jug. So let me first introduce Gary, who in turn will be, let me first introduce Jug, who will be in turn will introduce Gary and take the session forward. So Mr. Jug is Market Development Manager, Southeast Asia for the Nickel Institute. And he is currently based out of Singapore. Jug is responsible for market development activities in Asian market, outside Japan and China, executing projects, developing opportunities, and managing partner relations in the region. And he has got a very rich experience of more than 25 years in this field. And I now request Mr. Jug to take over the session.
Sachin, please make Mr. George the host. So if he wants to share the video, he can.
Thank you very much. Yes, let me try to share my screen. Nope, still disabled. Yes, now it works. Yes, I got it. Let me share it. I have to share the correct screen. Voila, you should be able to see now the first slide. Good evening to all of you. And a very special thank you to the IIW Mumbai branch for having us for today's webinar. As you can see, 4 common mistakes when choosing a corrosion-resistant alloy. This webinar is also supported by the International Molybdenum Association. I would appreciate if you would allow me to quickly introduce the Nickel Institute and IMOA to you. As you all might be aware, nickel is a key element in more than 75% of all stainless steel produced. It delivers the outstanding physical as well as mechanical properties. That's why stainless steel is such an attractive, easy to use and long-lasting solution. We are a global non-profit organization of the leading primary nickel producers. Our mission is to promote and support the proper use of nickel in the proper applications. Our headquarters sits in Toronto, where as well Gary is stationed. Then we have an office in Washington, and in Durham, South Carolina, the US, is our Science and Research Center. The European Center of Excellence of the Nickel Institute is in Brussels. There are 2 more incorporated offices, one in China, one in Japan, and then the 2 representative offices which are located in Australia and in Singapore. This is an overview of the members that are funding our organization. And of course, IMOA. And IMOA is like the Nickel Institute, a non-profit organization. It represents the majority of the molybdenum industry globally, and it promotes the properties and sustainable benefits of molybdenum in a wide range of modern-day applications. Molybdenum, as you are aware, is a key alloying element to provide improved corrosion resistance. Now our latest video creation. I let it play for a moment.
Nickel, chemical element Ni, atomic number 28, the fifth most common element on the planet. Shiny with a silvery tone, making stuff weldable, ductile, resistant to extreme temperatures. Hold up, you get it, it's pretty great stuff. But let's find out more. Nickel is all around, well, all of us. It's in batteries, buildings, turbines, tubing, coins, computers and gadgets. Your dishwasher, your kitchen sink, pots and pans, forks, spoons. I could go on, why not? You'll come across nickel at the dentists and the doctors, hospitals and your favourite restaurant. It'll be holding up the bridges that get you there, and it's probably in the transport you choose to use. Okay, you get the point. Nickel is a crucial component of all of our lives. I need it, you need it. It's even one of the 17 essential elements that plants need, but we need to make sure we produce and use it sustainably, in a way that helps our world. As with any mined metal, getting a hold of the stuff is energy intensive. Over the last 20 years, our members have achieved a 9% emissions reduction, but we know we need to do more. Nickel mining is evolving to become automated, safer and cleaner. All our members are committing to reducing their emissions and finding innovative new solutions such as fuel switching and low carbon electricity supplies to join the rest of the world in our shift to greener energy. And guess what? The nickel we produce is a vital part of this transition. Nickel is an essential enabler for all low carbon technologies. It has a critical role in wind, solar, hydroelectric and geothermal technologies. It's in electric vehicle batteries, electricity storage and hydrogen technology, as well as in carbon capture and sequestration techniques. So we're proud the stuff we produce can help play a part in the tech that's leading us to cleaner, greener energy. Nickel-powered green energy that can also help make our own production processes better. And did I mention that you can use nickel again and again and again and again and again and again, recyclable, endlessly. That's what I'm saying. So there you go. Nickel. Make stuff weldable, ductile, resistant to extreme temperatures, shiny, and getting greener by the day. Well, it's still silvery, but you know what I mean.
And now it gives me great pleasure to introduce to you today's speaker, Gary Coates. He's the technical manager for the Nickel Institute, and as mentioned before, he sits in Toronto, Canada. He has worked in the stainless steel and nickel alloy industry for 45 years, the last 21 with the Nickel Institute. Welding has always been a major interest, as often welding is the weakest link in fabrication. He has worked with many different end-use industries and with fabricators to ensure they have access to proper welding information. He is actively involved with many professional societies, including the American Welding Society, and he is an active contributor to the Welding Forum. He has made many presentations in India on all aspects of use of stainless steel and nickel alloys, and most of you know him already. With great pleasure, I'm handing over the floor to you, Gary. Thank you very much, and you all enjoy the webinar.
Thank you, Jörg, and it's always good to be back to make a presentation to such a great group. You have a very active group there in Mumbai, and that has an effect around the world actually now. So I think that is fantastic. So, okay, let's see if I can get to share.
Sachin, you have to reclaim host and then make host to make Gary the host, please.
Yeah, the new video is very interesting.
The video is kind of fun there, yeah.
Well made.
Oh, okay.
Thank you.
Maybe I'll take some inspiration for this for our new video for Sigma Weld, George.
You are allowed to do so.
Yeah.
All right. Gary,
Okay.
I think your screen is shared, yeah.
Yeah, okay, that's great. So today I'm going to talk about the some 4 different mistakes Some of them I have made myself, so there'll be some personal stories here on how to select a proper alloy and what not to do. So let's first of all just say, what do I mean by corrosion-resistant alloys? So for this presentation, I'm going to refer to them as all types of stainless steels. And of course, stainless steels contain chromium by definition, minimum of 10.5%, and their corrosion resistant relies on that passive oxide layer that is formed, and that is strengthened through a molybdenum and other alloying elements. Also included when we talk about CRAs or corrosion resistant alloys are the nickel alloys. So some nickel alloys contain chromium, just like the stainless steels, forming a passive oxide layer. But the important thing to remember is that some nickel alloys do not contain chromium, and therefore they don't form a passive oxide layer. They rely on the bulk alloying composition for their corrosion resistance. So let's get into the first mistake that I have seen made, and this is relatively common, and it is the misusing of the pitting resistance equivalent number. So I want to talk about what they are, how they should be used, and especially about how they should not be used, which I have seen them used for. So first of all, PREN is a tool for ranking of stainless steel alloys in their resistance to the initiation of pitting based on the most important alloying elements that affect the pitting resistance. It is really just an approximation of an alloy's level of pitting resistance for comparison purposes, and we'll go into those details later. We often think there's only one PREN formula in the literature which tries to compare the pitting resistance, but there are many different ones, and it depends on the tests, laboratory pitting tests that are done, many other factors that affect it. So there are different formulas. The most common one is the one you see here, percent chromium plus 3.3 times the percent molybdenum and half of the tungsten content. Now, only a few stainless steels contain tungsten, so a lot of people will leave tungsten out. It's really, there's one super duplex alloy that has tungsten in it, but it is roughly half the effect of molybdenum. And then a most important factor is the nitrogen content of the steel, and modern steel makers know how to add a little bit of nitrogen to the stainless steel. And I'll emphasize again, this is not nitrogen gas, and two, it's a monoatomic nitrogen N. So it behaves almost the same as carbon as an interstitial. It goes through the main metal atoms, chromium, nickel, molybdenum. They're the big atoms. Nitrogen and carbon are tiny little atoms that go between the bonds there. But there are other formulas. Some people have used nitrogen up to a factor of 30. There's some that have a positive factor for nickel. We'll see why in a minute. And some have a negative factor for manganese, because manganese can be slightly negative with pitting resistance. And just as some typical values, we know that 316L is better than 304L in pitting. So you can see the number, PREN number, is much higher on 316L. 825 is a nickel alloy, but relative low molybdenum content, it's even higher. The 6% molybdenum stainless steel, such as 254 SMO, 6XN, and there's other ones are much, much higher. And then some of the high alloyed nickel materials like a C276, if you use that formula, you get a very, very high number. So let's look at the effect of molybdenum and nickel, and the curve on the left is the effect of molybdenum content on an alloy, and it's measured in terms of pitting potential but we can say increased pitting resistance is really what it's measuring. 1% molybdenum doesn't do an awful lot, but 2% and 3% do very much for improving the pitting resistance. On the right is a curve for nickel. You can see the scale of the content of nickel on the bottom there, that there is a slight improvement in pitting with increasing nickel content, but nothing like what it is with molybdenum. So it is positive, but very, very small effect. And for that reason, it's left out of most PREN formulas. So one thing I want to next clarify is why there are different numbers quoted for the same alloy. You go to one paper, you'll see one number quoted for let's say 316L, another paper will show another number. Well, why? Well, because the PREN can be based on either the minimum content of the particular alloy, a mid-range, typical, or actual composition. So let's take 316L and the molybdenum content. In ASTM standards, the minimum molybdenum content is 2.00. That might be a fair number to use when calculating PREN. Typical today is somewhere around 2.05. We keep the molybdenum content at the very bottom. It is a rather expensive alloying element. You want to meet the standard, that is an ASTM, but you don't want to throw away extra, from a steelmaker's point of view, you don't want to throw away extra molybdenum that is not needed to meet the minimum specification. The mid-range is 2.5%, and some people will use that number, even though that is not really what is typically found today. And finally, you can use an actual content if you have a mill cert. You can actually use it, and that would be between 2.0 and 3.00%. And I'll just say that there are some European versions of 316L with 2.5% min moly, whereas ASTM and many of the specifications worldwide are 2.0 min moly. So the company that I used to work for was a European company, and we would often use the 2.5 because that is the material we were testing in most environments. But today it's really 2.0 min moly that is the absolute most common in the world. And this is just showing the minimum chromium content, the minimum molybdenum, minimum nitrogen content for 316L. And then we calculate the PREN numbers, and you can see they vary tremendously. If you use just the minimum alloy content, you get a number like 22.6. If you use the maximum content, you get 29.5. Typically, it might be 24.1, and that's the number I tend to use, or 24, just as a round, 24.5, something in that area I tend to use. So are the major alloying elements the only factor that affect pitting resistance? Well, the answer is no. There are many other factors that have major influence, on the pitting resistance, and that one of them is the content and composition of impurities, and manganese sulfides are the most detrimental. Today, many steel producers have a refining system that will reduce the sulfur down to 0.001%, very, very low compared to what it was before. But not all producers have that ability, and manganese is always in stainless steels as a deoxidizer. So when you have a higher sulfur content, you also have manganese sulfides present, which are very detrimental for pitting resistance. Proper heat treatment can be very important. The surface roughness and the final surface treatment, whether it was pickled or wire brushed or just left as is, that all affects the pitting resistance of a particular piece of metal. So in addition, we can say these formulas are based on tests done in acidic and oxidizing chloride containing media. They may not relate exactly to other chloride environments. If we have a neutral pH or a non-oxidizing system, so these PRE numbers may not relate directly to that. They may not be too far away, but they may not be directly relatable, comparable. And then we have the issue of bromides and iodides can also cause pitting, and there that it doesn't relate whatsoever to the PREN in any specific way, although it is somewhat related, but I would never use PREN to decide what to use in a bromide or iodide containing environment. So next question to ask is 316L, which we saw has a PREN around 25 or 24, always more pitting resistant than 304L, which has a PREN around 18. And the answer is no. And we have seen and documented where a 316L with a high manganese sulfide inclusion content, a rough surface finish, it can actually have a poorer pitting resistance in practice than a very smooth 304L with low inclusion content. And so you have to be very careful how you use PREN. It isn't a guarantee that one alloy is better than another. It may relate to the fact that one alloy is better if you compare the same surface finish, the same inclusion content, the same quality of heat treatment. Next question, can PREN tell me whether an alloy will pit in any particular chloride solution? And the answer is no. They're useful only for comparison purposes. You really need actual experience to properly evaluate if an alloy is suitable in any particular environment. Now, some of you who may work with seawater may hear, oh, if you have a PREN of greater than 40, it's suitable for seawater. Well, those kind of statements are very general, and that might be just normal seawater at ambient temperature, not hot seawater. It won't relate to the fact if you aerate the seawater or if you have turbulence that causes air to go into the seawater, the PREN of 40 may not be high enough. And of course, if seawater contains living organisms, you can get attachment of those organisms and then crevice corrosion underneath it. So even the general rules like PREN of 40 for seawater are very, very, very general rules, and you have to use them with care. The next question was whether do small differences in the PREN have significance? And as you know, here I'm thinking of something in the difference of 1 or 2 in number. They have little meaning because other factors are important unless you compare exactly two materials of the same surface finish, inclusion content, etc. And so be careful if an alloy supplier comes to you and says, my alloy has a PREN of 2 higher than my competitor's material. That may not mean anything at all. Can PREN ranking be used for nickel alloys? Well, there is some moderate validity for comparison purposes to the nickel chrome moly nickel alloys, such as the C-type, C276, C22, alloy 59, etc., and the nickel chrome moly iron alloys, the ones that have a higher iron content, such as 625. It's not exact, it's not as good as it is for stainless steels, but it's not bad. It gives you an indication. However, with the non-chromium containing nickel alloys, it has absolutely no meaning whatsoever. So don't ever try to use it with a Manel 400 or a nickel 200 or a copper nickel alloy or a nickel copper alloy. Can PREN numbers tell me anything about the propagation rates of pits in an alloy? And again, the answer is no. Other elements such as nickel, which are not in the PREN, have a major significance in reducing the propagation rate. And you have to remember at the bottom of a pit, the pH and the chloride content are much higher than in the bulk environment. And so therefore it's a very different condition. And PREN is measured on the initiation to pitting, not the propagation of pitting. And this slide on the right, or this picture on the right, just shows the fact, and it's really the top one where we have the round circles, where we have essentially a 316L type alloy that the nickel content, as we increase it, will drastically reduce the corrosion rate. Here we're actually measuring it as crevice corrosion, but the environment in a crevice will eventually be the same as what it is in the bottom of a pit. So it's a very comparable way of looking at it. Can PREN be used for comparison of crevice corrosion resistance between two alloys? And the answer is there is a general correlation. So if the PREN of one alloy, alloy A, is higher than alloy B, most often the crevice corrosion resistance of alloy A will be higher than alloy B. But the difference between the two alloys can be significantly different. And so we've seen it where, for example, the pitting resistance of alloy A is much higher than alloy B, but the crevice corrosion resistance of alloy A is only slightly higher than alloy B. And so you have to be careful when using it in terms of pitting and crevice corrosion resistance, but it's somewhat close. Can PREN ranking be used for other corrosion types? For example, general corrosion, and here the answer is no. There's a temptation to do it, and this is really the most common mistake that I see being made by people who, they like the fact that it's a number. You can easily compare numbers. And so they want to use the PREN number for comparing in other corrosion, general corrosion in other media. But it can be completely wrong. But some media, there is a good correlation. So for example, if we take weak sulfuric acid, 316L, is more corrosion, general corrosion resistant than 304. So it actually works there, even though it wasn't intended to be used that way. But if we take 98% sulfuric acid, 304 is actually slightly better than 316L. Both may be suitable, both may be used, but the PREN number doesn't give anything. In fact, it actually gives a wrong indication there. How should I use PREN? So we've seen a lot of ways it shouldn't be used. Well, as we say, it is used for ranking different stainless steels to initiation of pitting. We've seen the limitations, and really it should only be used as one tool together with several others, and that includes practical experience, other testing to help select an alloy. So we know that the 6 moly stainless steels have a significantly high PREN than 317L or 904L, and of course 316L. So that sort of helps us to center on if we got a very severe environment where 316L has pitted very badly, we can sort of say, okay, well, the 6% moly should be fine, but let's investigate it further to make sure that it will be fine. As we said, there are many other factors that affect an alloy pitting resistance. So what about welds? This is a welding group, and we have to remember that welds have many small imperfections. Slag inclusions, even if they're not large, if you look under a microscope at say 50 power, you will see that there are tiny little slag particles that might be in the surface. There's other inclusions, porosity can exist, and again, it may only be seen by if you look at it, a high enough power, heat tint, micro cracks, they all affect pitting resistance. So the weld metal may not be as, in practice, may not be as pit resistant as the base metal, and therefore that does limit the use of PREN. And I just also want to mention about autogenous welds, welds without filler metal. For stainless steel, the higher the molybdenum content in the base material, the more the molybdenum is susceptible to segregation in the autogenous weld, and the weld without filler metal. And segregation of molybdenum means lower corrosion resistance. Many of you are familiar with the curve that was generated years ago when I was a young corrosion specialist by a friend of mine, Dr. Andrew Gardner, and where 316L in the blue arrows here, the top line is the unwelded sample, so the base material unwelded. The line here, intermittent line here, is the autogenous weld resistance. So for 316L with 2% molybdenum, the difference between the base metal and the autogenous weld is small. When we get to 904L, which is the red arrows here, the difference becomes a little bit larger, and certainly any environment that 904L, if it's used in, has chlorides and where pitting is expected, you really should not use autogenous welding. And for the 6% molybdenum alloys, 254 SMO, Al6XN, for example, there is a huge difference, as these orange arrows show, and you should never, ever allow autogenous welds unless they are annealed afterwards. Annealing will restore the uniform molybdenum content in the material, so molybdenum that has segregated will diffuse back, and you'll regain the corrosion resistance, the pitting resistance. And I'll just want to emphasize, these apply to autogenous welds only. If you have filler metal, it's a completely different picture, and with filler metal, the filler metals are compensated, so they give corrosion resistance very close to the base metal. Maybe not the same, but very close. Well, that's enough about PREN. I'm going to move on to the lack of knowledge of contaminants. And so, for example, if you've been asked to select the most cost-effective material for a process, and the process engineer says it contains, let's say, 20% acid, sulfuric acid, balanced water, 40 degrees C, there's nothing else in there. Can you select an alloy based on that information? And the answer is no, you don't want to do that. There are always contaminants in the process solution. They may not be important to the process. So the chemical engineers may not care that there's some chloride there. They may not care whether there's any other ions, ferric, ferrous in there, other hydrocarbons, whatever. They may not be important to him, but they are important to the corrosion specialist here. And corrosion tables and isocorrosion curves generally assume quite high purity chemicals. So you have to be very careful with them, because industrial solutions do contain impurities, and those impurities can either increase the corrosion rate or they can decrease the corrosion rate. So they can have different effects depending on the impurity. So let's look at the, this is the isocorrosion curve for 316, for different stainless steels and sulfuric acid. The one in red here, I've sort of painted in with the, with PowerPoint, and I don't have a steady hand, so it's a little bit not quite the same as the original curve, but it's close. You can see that there's a limited range of usage of 316L in dilute sulfuric acid. You get up to 20%. You you can only use it at essentially 20 degrees C. As we get higher in temperature, the amount of acid it will tolerate is less. And so this line represents a corrosion rate of 0.1 millimeter per year. Underneath the line is less than 0.1 millimeter per year. But if we have a small amount of ferrous or ferric ion or any other oxidizing ion there, it extends the use of that of 316L. So even if we have a little bit of 0.05% ferrous ion there, you can use 316L at close to 35% acid, as long as you maintain that amount of oxidizing ion at, this is at 20 degrees C, you'll be fine, but you have to maintain a minimum of that level there. Most of the data that is generated is based on just a normal amount of air, oxygen in the solution. And if we aerate it, it will result in a lower corrosion rate, useful at higher concentrations or temperatures, just like that, those ferrous and ferric ions. And if we de-aerate it, take out all the oxygen there, you get a smaller range. So here is the a curve. So the top red arrow shows 316 with where we air saturate it, we blow air into the material, and again you get a much higher useful range where you can use 316. If it's normal air content, it's this line, the same line we looked at earlier. And if we de-aerate the solution, 316 is used at a much smaller area there. So maybe 10-12% for air free de-aerated sulfuric acids. Other contaminants can increase the corrosion rate of, and I'm using sulfuric acid as an example here, but most other acids, chlorides, and we can see here, and this is tests I did years ago, and 10% sulfuric acid at 60 degrees C. 316L was actually passive with zero chloride in the reagent grade sulfuric acid at 10%. But the moment we added just a tiny amount of chloride, the corrosion rate went from almost nothing up to 1 millimeter a year very quickly. In other alloys, they had longer, they could tolerate more and more amounts of chloride, and here 904L with the highest molybdenum content tolerated the highest amount of chloride, but even with sufficient amount of chloride, it also became active. And this is active corrosion, so it isn't pitting, it's high corrosion rates there. So you have to be very careful with chloride, and the curve on the right, just another way of presenting the same information based on the temperature, where the one on the left was 60 degrees C, this puts the temperature as one of the variables. Fluoride is also very dangerous, increasing the corrosion rates. We see it a lot in phosphoric acid and is one of the key contaminants to increase corrosion rate. Very important to know the fluoride content in the phosphoric acid. And iodides and bromides, they're less common, but also very dangerous as contaminants. So a true story, when I worked with a stainless steel producer, distributor, our sales desk had received an inquiry for about 25 tons of 904L plate. At that time, it was worth almost $250,000. Of course, the salesman was very excited. There are very few producers of the alloy at the time, and we were expected to get the order. But the customer did want to talk to me to confirm that 904L would be satisfactory for that particular service environment. Well, as it turned out, I reviewed the conditions. The acid had a lot of oxidizing contaminants in it, and I decided that 316L would actually perform very well there, and because they guaranteed that those contaminants would always be there. This was just part of the process. They were always adding it, and so I suggested that he could use 316L, and as a result, he did buy it from us. Actually, there were many more competitors for 316L, but of course there were some unhappy salesmen in the company because there was this big order that they were hoping to get, and 316L is maybe 1/3 the cost of 904L. However, the president of the company actually supported my action, and the customer became very loyal to us. So those of you who are in the sales side, I always believe it's important to be straightforward, honest with your customers, tell them exactly what the situation, and the next time, if he was going to use 316L and particular circumstances required it to use a higher alloy, he would have believed me. So he would have trusted us that we were telling the right story there. So I probably, if you were listening to any of the earlier ones on the nickel alloys, well, the nickel molybdenum alloy contains no chromium, works well in strongly reducing chemicals such as hydrochloric acid. Here's an isocorrosion curve, and even the boiling solutions of hydrochloric acid, the B alloy performs very well. So early in my career, a fabricator had built a drainage filter for his customer in 316L. What he usually built it in, it lasted only 3 months. He then went back and he realized that it was corroding because there was a lot of hydrochloric acid in what was going down the drain. He did his research and found that the nickel alloy B2 was the best alloy for hydrochloric acid, and I agreed that it was actually very good in pure hydrochloric acid solution. He went ahead, and it's a very expensive alloy, about 10 times the cost of 316L, and he fabricated the filter, and guess what? It lasted 3 days. Why? Well, because the B alloys, they contain no chromium. They're very poor in any oxidizing conditions. So as it turned out, there were oxidizing ions in the drain stuff that went into the drain. The picture on the right shows that at even up to 10 parts per million ferric ion, it really didn't have a lot of effect, but above 10 parts per million, the corrosion rate starts to skyrocket. So you have to be very, very careful with these kinds of alloys. They're excellent in constantly reducing conditions. They're not so good in oxidizing conditions. When it comes to water, always ask for a full chemical analysis, and a full chemical analysis will have maybe 40 or 50 elements in there. Most of them are going to be near zero, but you really want to know what are in there. On the right, I'm showing just something of it from a case that I was looking at late last year, and they went over everything, and we could then identify what the problem was in there. So always ask for a full chemical analysis there. And on top of that, if the water is going to be chlorinated, we want to know that, and if it will be chlorinated at all times, even if the system is shut down and if it's not drained, because we're really worried about microbiologically influenced corrosion there too. So most corrosion tables won't even mention MIC corrosion, so it may not be top of mind when you're thinking about it. But if If the water is supposed to be chlorinated, but may sit there for a long period of time, the chlorination disappears with time. Microbes can grow and cause corrosion of stainless steels. So moving on to the third one, it's really the lack of knowledge of actual equipment operation. And again, the process engineer, if he tells you that the equipment operates at a certain uniform temperature, maybe a range of temperatures and concentrations, and he tells you the contaminants, and should you select an alloy based solely on those parameters? And of course, the answer is no. And you need to ask a lot more questions. So for example, you need to ask, well, what happens if the concentration of anything in there increases or decreases slightly, or the temperature increases due to upset conditions, not intended to happen, but can happen? What the likely fluctuations are in cooling water temperature. If in one season the water that you're getting from whatever the water source is cool, it may work fine there, but if the water is hot, it may not work there. So we really need to know both the process well and the materials. And the one case I take here is with one of the duplex alloys, and here it's this is an iso-corrosion curve and sulfuric acid for a higher alloy duplex alloy with both the 1 mil per year, 0.001 thousandths of an inch, or 0.03 millimeter per year. You can see the line for 50 mils per year, 50 times that amount, is just slightly higher, so that if the temperature increases 5 degrees, which normally shouldn't be a problem, you get a 50 times increase in corrosion rate. Or if you increase the concentration slightly by a few percent, you will also get into that range. So you have to be very careful. And whenever I look at iso-corrosion curves, I want to see more than just the one line. Most iso-corrosion curves show maybe 0.1 millimeter a year or something in that area. I want to see more lines on that curve. With stainless steels, you need to be careful, but especially duplex stainless steels, they are more sensitive for going from the passive state to the active state, and with relatively high corrosion rates in the active state. This is iso-corrosion curve for sulfuric acid. It's for the C22 alloy. And there you can see here, it's 5 mils per year, 0.13 millimeter per year. And you can see to get up to 5% increase in, or 5 degrees C increase in temperature will not mean a lot. 10 degrees C might mean a little bit more, but still it doesn't corrode as quickly as the duplex alloy with the same change of temperature or concentration. So I like to see curves like this, so that it gives me more confidence that if an upset occurs, the material is not going to start corroding very, very quickly. We also have to think about differences in corrosion rates in the immersed condition of the material, right at the liquid level line, or in the vapor phase, and they can vary considerably, or they could actually be similar depending on the environment. So for the one case I take here is a supersaturated brine solution. This is with potash, calcium chloride solution. In supersaturated brine solution, there's very little oxygen in the solution, especially if the temperature is above 80 degrees C. Oxygen is, of course, a driving force for pitting as well as chloride stress corrosion cracking. Take the oxygen out, the even 316L will work fine. So this particular tank stored hot potash at 110 degrees C, and they used 316L because it was fine in the immersed service. But where it was right at the liquid level line, of course, you have higher oxygen content there, and you did get pitting. And so the liquid level line varied in this particular tank about 600 millimeter, and as liquid was added or taken from the tank. And so what they did is they installed a lining of 2205 in the liquid level line. It was about 620 millimeter wide sheet there, and that solves the problem there. So they kept the 316L tank because it worked in 90% of the applications fine. A second case is in hydrofluoric acid, a very, very nasty acid, and and we know because the nickel copper alloy 400, which is the most common alloy used, or one of the most common alloy used for this service, it's important to ensure the liquid was free of oxygen. The company knew that, but they didn't think about the vapor phase. And the top red arrow here shows in the vapor phase very high corrosion rates, depending on the acid concentration. The second red line is the middle one there, is that interface or liquid level line mixture of both liquid. Sometimes it was in the liquid all the time, other times it was in the vapor part of the time. And finally, the continuously immersed exposure there. So you have to be very careful. And in this case, it was extra special because the alloy 400 will stress corrosion crack in aerated hydrofluoric acid or in the vapor phase. So really we need to ask more questions. What happens during startup, shutdown conditions, and those of you who work in oil and gas know about polythionic stress corrosion cracking. You can get that forming during shutdowns where hydrogen sulfide is in a gas. There's oxygen and moisture in the gas. It will cause stress corrosion cracking of sensitized stainless steel. So we're well aware of that as corrosion people. Not everybody is aware of that. Sometimes, especially when we talk about food or pharmaceutical or even the chemical industry, the cleaning solutions used to take deposits off pipe or the tank walls, they can actually be more corrosive than the material being handled by it. And so therefore, you really need to get into things like, how are we going to clean it? How are we going to disinfect it? And always important to ask about the process changes in the near future, whether they will occur, whether the conditions given will be expected. You may want to increase the productivity after a while, increase the temperature, increase concentrations. So you may want to be very conservative in your material choice if you think that things may change. And process engineers love to change things to make them more efficient. Finally, mistake number 4, I call it secrets from the fabrication shop. And so question, the fabricator says he makes stainless steel equipment regularly. He does. He should have no problem fabricating my equipment. And again, that's not necessarily true. And you can easily run into trouble by assuming that. And there are many different quality levels in stainless steel equipment based on the industry. You can imagine structural uses, obviously strength and ductility are some of the major issues there. Chemical, petrochemical, it is corrosion resistance primarily, maybe heat resistance there. The quality inspection is important. Food, pharmaceutical, nuclear, they all have different levels of quality acceptance and inspection. And one should always remember that who gets the order to fabricate your equipment? It is always the lowest bidder. So it's important to make sure that the lowest bidder understands what you actually need in terms of quality. And so obviously, and we do this for high-end work, inspecting the fabrication shops to qualify it. And we found this is important in many industries, because you're really telling the purchasing people, you can go to these shops for quality fabrication of this particular component based on the quality level needed. You can't go to these, even though they may offer a much lower price. So inspect it. It may be hard during COVID to do that is a face-to-face, but I like to go to plants and have a look at what they're doing. I like to talk to shop personnel, the welders, the equipment operators, the foremen. You can learn a lot about their capability, how they handle new materials, special welding procedures, that sort of stuff. And when you do get into some of the special alloys, whether they're duplex, 6-moly, nickel alloys, you really want to see how they have handled similar alloys in the past, whether they're, how much time they spend investigating what they need to do to ensure a quality product. And most fabrication shops, most of you know who are inspectors, if you go in there and you say, oh, can you weld 6-moly stainless steels? They'll say, well, of course we can. And then you can say, have you ever done it before? No, we've never done it before. You know, and they ensure it is possible for them to do it if they actually thoroughly investigate. But usually they don't investigate before they quote thoroughly. And sometimes they underbid and then they have to take shortcuts. So let's talk about the purchase of the stainless steel or nickel alloy. And typically 304L, 316L, there are no extra specifications required. But for duplex alloys, the standard ASTM A240 does not call for any extra quality testing on the alloys. You have to specify it extra. And whether it's the A923 or A1084 or the ISO 17781, they all need to be specified, and even which tests need to be done, so it is very clear. And although many quality producers do this test as standard, some do not. So my next story is about a friend of mine, an inspector. He went to a shop, and I won't say which country it was in. It wasn't India, I'll tell you that. But he was representing the end user, meeting at the fabricator shop after fabrication had started. And the alloy producer was there, and the inspector asked the alloy producer, he said the 2205 alloy was required in the specification to be tested to ASTM A923 practice C, which is the minimum corrosion test that you really need. Where are the test results? And the supplier, the producer said, all our 2205 meets that requirement. If you test it and it doesn't pass the test, send it back to us and we'll replace it. Well, of course, that would be, you know, once you've started fabricating, once you've got the material, you know, you don't want to, you're not going to test it to start with. And if you did test it because you thought something was wrong with it, that sets you back in time and all the work you may have put into fabricating up at that point. So the first thing to do, obviously, is deal with a reputable supplier that does the tests and make sure when the material is delivered that all the tests are done properly, inspected thoroughly. For the 6-moly alloys, the heat treatment is critical. The heat treatment temperatures in ASTM are at the minimum, and some of them, if you use just the minimum, they will not actually give good quality results. So it is, I would say, important to check for corrosion resistance. And there, for example, the ASTM G48A ferric chloride test at 40 degrees C is a good idea to have. With nickel alloys, it's actually even worse situation, and we're running into problems with certain suppliers who don't know how to make it properly, but they can easily meet the ASTM specifications. So for example, B575 is one for most corrosion-resistant materials. They don't even require any aspect of refining, and there's reasons for that. I won't go into it. You put a corrosion test on it. There are standardized tests that you can do, but there's no acceptance criteria. And for that reason, MTI, the Materials Technology Institute, has done a project to determine typical values from quality suppliers. And this was one of the reports from 2017. We've since done 10 more alloys. That was only 5 alloys. We've done 10 more alloys. So, and what about welds? Do you want to do a corrosion test on the PQR? You know, what about the welder qualification? The welder mostly thinks that if he passes his bend test, maybe a tensile test, that he's done it properly, but it's easy to do, pass those tests and have a poor corrosion resistance in the welds. And does he really know what is important to make sure the corrosion resistance is maintained? And even on production welds, as if you're an end user, you might want random tests on production welds using a runoff tab, for example. And this is especially important with duplex and super duplex materials more than many of the austenitic grades. And finally, heat tint, that's always the question that we need to answer. How much heat tint is there on welds as welded? Should it be removed? Most people remove it on the outside of a vessel where it has probably the least amount of significance. They may not remove it on the inside. And then how do they remove it? And that, of course, is a whole separate webinar in itself. So in summary, I've chosen 4 common mistakes, things that I've run across, I would say, relatively regularly. And many of these mistakes relate to not asking the necessary questions, not specifying what is needed on fabrication. And hopefully you have learned something from these presentation and will avoid making these mistakes. So thank you very much. And if we have time, we can take some questions now.
Yeah, Gary, I think there are 13 questions in the Q&A.
Oh, okay.
So we can take one by one.
Yeah, I see some of them here. So does Nickel Institute have corrosion charts similar to Sandvik and Autocomp corrosion charts? We do not. We use ISO corrosion charts or corrosion charts that we consider valuable. We do have some, not corrosion charts, but corrosion information that was generated by International Nickel Corporation, INCO, back in the very early 80s, 1970s, 1960s. We have a number of publications from them on our website that contain information that is not contained anywhere else. You can go to our website and, for example, if you're interested in sulfuric acid, go into the library, search on sulfuric, and that information will come up as a PDF of the publication. The publications are all searchable there. And next question was, is PREN only applicable to chloride concentration environment? And that's right. It's only chlorides that PREN is applicable to, and the environment will determine how what number of PREN as a minimum you may want to have there. Next question was, most of 316, 304 material certificates don't have PREN number. Is it mandatory to be present? And the answer is no, it isn't mandatory. Sometimes nitrogen is not reported on the mill test certificate either. In most of the ASTM specs now, it is. Nitrogen is mandatory, but you can calculate what it is from the actual composition. It's an easy calculation. Some of the duplex materials, and especially super duplex, they do require you to report PREN, and some of the producers want to report the PREN, especially on super duplex, where there are many specifications that say PREN minimum of 40 or 41. They want to show that. And I think the ISO spec requires you to report PREN numbers too, but those 304, 316, 317L, 904L, most of the grades do not require that. I think a couple of the 6 moly grades may require you, again, because they have a PREN minimum of 40, they will report that. And that is based on actual composition. But as I say, that's only part of the story, the heat treatment, the inclusion content. To what extent can PREN or corrosion resistance be improved by enhancing the surface finish? Well, you can enhance it. You can enhance the corrosion resistance considerably. And if you want to do a trial, you can take something that has an 80 grit surface finish, compare it to something that has a 600 grit surface finish, and you can see a large difference. And you see this in the food industry, where both with 3A specifications, which are coming out of the US, or ones coming out of Europe, they will actually specify a minimum surface finish on the steel to be used for food contact surfaces, because they know the surface finish is very, very important there. Is PREN only considered under stagnant fluids? Yes, that's a good question. If I have seawater flowing at over 1.5 meters per second elevated temperature, I can use 316L, because you will not get pitting with high velocity seawater. But if you have seawater flowing at less than 1.5 meters per second, then, or if you have stagnant conditions when a system is shut down, then pitting is of concern. It really isn't PREN, but it is the pitting resistance here that we're talking about. I'm not sure I understand that question. I'll just go to some other ones here. We'll try to answer all the questions eventually later. What should be the corrosion rate acceptable in mils per year, or millimeter per year for that matter, in any environment? And really the question comes that it depends on what you have. If you have a rupture disc that's 0.1 millimeter thick, obviously you don't want any corrosion rate on it. But for any thicker material, the general corrosion rate, we would say typically we aim at is 0.1 millimeter per year, or 4 mils per year as typical, but it really depends on the environment. And you also have to think of, if you have a corrosion rate, you are contaminating the solution with the corrosion products, and that may have an effect on what corrosion rate you allow. So it really will depend on the particular environment. can I use ER307 in laser cladding for impurities such as slurry contaminants, which contain hard particles? So 307 is a high, relatively high strength, but it also is used a lot in the armaments in resisting impact of bullets and things like that. So it is better in a slurry containing hard particles. It's not bad. What we do have to look at though is whether there's a corrosive element there. So let's say that you have a slurry environment with hard particles, but it's also at a acidic pH, and let's say it's at pH of 4 or 3, that makes the combination of corrosion and abrasion, they're synergistic, and it is possible that 307 is too underalloyed for that particular kind of application, whereas if it were neutral solution or a slightly alkaline pH, 8, 9, 10, the 307 would work good. I won't say it's the best alloy, but it's not a bad idea for that. Although I don't know, you'd have to have some experience with hot cracking resistance. The 307 is susceptible. It's a fully austenitic alloy susceptible to hot cracking. Okay, there was a question about the literature to the pulp and paper industry. We probably have the best publication that's relatively short on the pulp and paper industry. We can send the particular number from it, but if you go to our website, the Nickel Institute website under the library and just use the word pulp as a search word, it will show up, and it talks about stainless steels, nickel alloys, and even we talk about titanium a bit for the pulp and paper industry in there. And it is really, we find, the best piece of information on that subject. There are more research books there, but it's really a great book. And we revised it, I'll say it was 4 years ago now, so it's fairly up to date. Will the type of shielding gas or backing gas affect PREN? Yes, it definitely will. It won't affect the PREN, the number, but it will affect the pitting resistance. Of course, the shielding gas, if it contains oxygen, you'll get oxide on the surface, and that will reduce, or oxides even in the weld that don't come out, trapped in there, and that can affect the pitting resistance. You can actually even put a tiny amount of nitrogen or nitrogen oxide in, let's say a MIG shielding gas, and that also improves the pitting resistance. Is done in some of the duplex alloys, especially. But it doesn't affect the PREN, but it does affect the pitting resistance. And again, the backing gas, if backing gas has less effect, except for oxygen, where you oxidize the weld, and that if you have too high oxygen in the backing gas, you get an oxide on there, and that lowers the pitting resistance. You can use argon, and generally we find that people will use high purity nitrogen too if it is less expensive as a backing gas for TIG welding, and that works. That will work fine as long as you remove the oxygen that was there originally. How many times can we do pickling and passivation after fabrication? That's a tough question. You can always repassivate, and repassivate we talk about with nitric acid or citric acid. That does not actually remove any of the stainless steel material. It will remove free iron contamination on the surface. Pickling, you do remove a tiny amount of metal, a few microns of metal if it's done properly. There's always a danger of over pickling. That's the word I wanted. Pickling too much where you actually attack the grain boundaries of the material. So you have to be a bit careful with that. But theoretically, if you do it under the right conditions, you can pickle it many times. And if you use a pickling paste, for example, it has just a limited amount of hydrofluoric nitric acid in it, and it is almost impossible to over pickle an austenitic stainless steel. How do you choose the post-weld temperature for duplex stainless steel? Generally, we say don't do any post-weld heat treatment on duplex stainless steel because you are have a hard time picking a proper temperature. If you have to do it, you want to do a full anneal, which is roughly 1030 degrees Celsius. You really want it to heat up relatively quickly to 1030 and then water quench it afterwards. And that can cause distortion. So distortion is not a good thing to have, of course, when you water quench it. Easy to do on a pipe or plate or something like that, but on a fabricated component, it's difficult. If you have duplex and let's say a chromoly or a higher carbon steel in there, and the code requires you to stress relieve the carbon steel, that is tricky, and typically you do it knowing that you impair the duplex stainless steel slightly, and I would recommend testing to ensure that you simulate it, do a trial piece before you do the real piece, and make sure that the duplex stainless steel is not impaired properly, or not impaired so badly that it affects its performance. It's a big topic, but it has been done, and I'm struggling here to get the temperature. I believe it's around 1050 Fahrenheit, which I'd have to think about in Celsius there, but it's sort of in an area where you don't get the 475 degree embrittlement of the duplex, and you don't get too much intermetallic phases that you get at the higher temperature. So it is a compromised temperature. We observed cracking in weld at site. However, job was laying at site for 6 months under atmospheric conditions. What is the reason for cracking? Well, I really need to know what alloy is being welded there before commenting on that. But there are alloys that you can get micro cracks in the weld that aren't easily detected either by dye penetrant, liquid penetrant testing, and then when they sit for a while, whether they will open up. But really need to know what alloy is involved there. Can intergranular grain boundary corrosion patterns be found on weldment microstructure after G28 test? So G28 is what we normally use on nickel alloys, and you can, if the material is bad, yes, you do get a intergranular grain boundary corrosion on them, and again, I'd be interested to know what alloys we really want to talk about there, but The welds themselves shouldn't I'm going to be careful here. In the last MTI study where we did G28 tests, welds typically have a higher corrosion rate than the base material typically, and we haven't established what is a good corrosion rate. However, when it's a dendritic structure, it normally doesn't intergranularly corrode that easily. So I'd be actually interested to hear more what you have found there. Any chart on selecting a right material there, don't try to find a chart. You really need to know the material, you really need to know the environment, and most charts like the Autocompu Sandvik are sort of the best, absolute best for stainless steel, but they talk about high purity materials. They will help you, point you in the right direction. Don't ever select a material based solely on that. You need to know a lot more behind the impurities there. Oh, sorry, somebody. Okay, so the delayed cracking, okay, sorry, the inquirer said the material is 410 stainless steel, 410S, which is a weldable version of 410, still can have relatively high carbon, so you can still get some martensite formation. 410S is often welded with an austenitic stainless steel rather than a matching filler metal. It depends a little bit on the application too there, but you can get brittle areas, especially in the heat affected zone. But 410S, if it is welded with 410S, then you have to be careful with the preheat and post-weld heat treatment temperature. And when I say that, it's not a high temperature. It really depends on the actual carbon content of the 410. If it's 0.08, which is the maximum for 410S, it'll be a higher temperature than if the 410S is 0.04 carbon. You still like to have a little bit of preheat on it, and a post-weld treat with a slow cool can be helpful. Again, depends on the carbon content. Welding a 410 is tricky because the carbon content can vary all over the place on it. Could you please give possible reasons for low ferrite content in the weld metal? So we're talking about duplex here. How to achieve the ferrite measurement above 40 to 50%. Okay, especially in weld mid thickness. So let's talk about I presume we're talking about duplex, and I'll say it's 2205 for argument's sake here. Oh, super duplex. Sorry, underneath he adds that it's a super duplex material. So the filler metals for super duplex stainless steel have a higher nickel content than the base metal. Depends on whether it's the shielded metal arc welding or flux core or bare wire. And the reason for that is that to have too high a ferrite content is far, far worse than having too low a ferrite content. And I use low because people generally say, well, 40% is what we aim for in the base material. But in the weld material, most people will allow down to 30% ferrite in there, and sometimes even 25% ferrite. So 40% ferrite in a weld metal is tough to get, especially with coated electrodes, shielded metal arc welding. because it has the higher nickel content. Nickel promotes the austenite formation there. So if you're getting 35% ferrite in a super duplex weld, there's nothing wrong with that. I mean, I would say don't worry about that, or the end user shouldn't worry about that. That is perfectly fine. 30% is often acceptable. People often set 30% as the minimum in the weld. I'd have to check the ISO spec whether that is actually what they have as the minimum there. In cryogenic service, turbo machinery using aluminum alloys. I've seen. What does that mean? Well, it's about aluminum and stainless steel for cryogenic service, and aluminum alloys are very ductile at low temperature. So is austenitic stainless steel, whether it's 300 series and most 200 series. They're very good at the very, very low temperature. Sometimes aluminum is used, or aluminium, if you like that pronunciation. I've used the American one, but aluminum is lighter in weight, and if weight considerations are a factor, it may be for that reason. And I know when we were building, the company I was working with was building LNG tankers, at least the spheres for that LNG was stored in for ship tankers, and they would use aluminum or actually 9% nickel alloy for them, depending on whatever was cheaper. If aluminum was cheaper, they'd use aluminum. If 9% nickel steels were cheaper, they'd use that. Stainless steel is better in some ways, especially as we get down to liquid hydrogen temperatures. But I'd have to actually see what the actual application is there. But aluminum is a good material for cryogenic applications also.
Gary, you would like to stop here and take the questions later? Yeah, so that I can compile all the questions to send it to you.
Yeah, sure,
Because
that would be fine.
Yeah. What I can see is the number of questions are increasing. People are still
With Gary, the problem is people always want all the answers at the same time.
Yes, exactly. Yes, no, we'll work to get you the answers to everything here. Yeah, because there are many very good questions here.
Right,
yes.
Right. So, Nimesh, you would like to conclude?
Thanks a lot, Gary, for the wonderful session. And it's as usual, people really get a lot of insights from your practical experience, and it's so insightful that at times really not so much of a concern. And you are really helpful in the answers. I think it really helps people with the way they would like to understand and get a lot of clarifications. So thanks a lot. It was a lovely session. We look forward to really a few more. I think you mentioned at certain places, I have noted it down, that this is a topic for another webinar. So we'll come back to you with those topics and try and schedule one more WeldTech talk. And thanks,
Yeah,
George.
no, I'd be glad to do another one. Thank you. I always enjoy coming and presenting with you guys.
Yeah, thanks to both you and Jug, for this cooperation. We really look forward.
Yeah, and